The quality level seen by the customer of our value stream is one of the most critical process metrics. This quality level is the result of all the defects generated by the different process steps as well as those coming from the parts suppliers. Ideally, defects should not be produced in the first place. Unfortunately, the state of the art, in many technologies, is still not there. Therefore, in the meantime, we need process tests and controls to catch and correct defects as soon as they are produced. In our value stream map we focus on process flow, but this flow is very much affected by quality. It is important to find out where in the process each type of defect is generated and where in the process it will be detected to make sure it doesn't find its way to the customer. Download this Excel file from OneDrive to your PC. It is an example of a board assembly value stream to illustrate a typical control plan. The control plan defines all the controls, visual, test, etc., installed along the value stream in order to catch the defects as soon as they are produced, in order to correct them, and give immediate feedback to the step producing them. These controls have a cost, both in terms of manpower and flow drop, so they should be minimized and installed just where and when they are required. As the process is improved, by solving the root cause of the defects, controls can be removed or installed somewhere else. The control plan is, therefore, a living document. Defect contributors are defective components coming from suppliers and defects from the 4 process steps. SMT, surface mount technology, automatic component placement. Reflow solder of these components. Manual PTH, pin through hole, component insertion. Wave soldering of PTH components. Defects are detected on several visual inspections along the process. ICT, in-circuit test, at the end of the assembly process. Final functional test. Defects per unit, DPU, is the metric that interests the customer, but it's not very practical as a process metric, because we are typically producing products with very different levels of complexity. Some boards may have just 5 components and others 500. Defects per million opportunities, DPMO, is a useful process trick that is independent of the product complexity. This metric will allow us, for instance, to know if our soldering process is improving or getting worse, with independence of the complexity of the products. In this example we have 1 defective component in 3 boards, so DPU is 0.33 defective components per board. When we measure in DPMO we must define the OFEs, opportunities for error, of the process we are dealing with. In the component placement process, OFEs equals number of components placed. In the soldering process, OFEs equals number of solder joints soldered. In our example DPMO is 27,777 defective components out of every million placed. Each type of process has a state-of-the-art DPMO, that is the best DPMO being achieved in the industry for that process. This can vary widely from a DPMO of 10 in a highly automated robust process to a DPMO of 5,000 in a manual process highly dependent on an artist's skill. For this reason DPMO values can't be compounded from different processes with different OFEs to obtain an overall DPMO. DPMO is only useful to the process owner to know if the process is improving or to compare it with similar processes. This metric has no interest for the customer. In our electronic assembly example, we have 500 SMT components and 100 PTH, therefore these are the corresponding OFEs for the placement and insertion operations. Total components used per board is, therefore, 600. The 500 SMT components have a total of 1,500 solder joints, therefore, these are the reflow solder OFEs. The 100 PTH components have a total of 300 solder joints, wave solder OFEs. Process DPMOs define the quality of our different process steps, and the OFEs are specific for each product type. The DPMO values for each process step are obtained from historical data of this process. There could be large differences between different board types, depending on the mix of large and small components in the board. On each step we can estimate the expected defects per unit. DPU is equal to DPMO times OFEs divided by 1 million. Since the types of defects contributed by the 5 different sources are independent, the total number of defects produced will be sum of each defect contribution. Total DPU is the sum of all DPUs. Process yield is the proportion of defect-free units when tested. If defects are independent, DPU follows a Poisson distribution, so yield and DPU are related by yield equal to e to the power of minus DPU. For instance, an average of 1 defect per unit will still produce 37% defect-free units. There will be units with more than one defect. Total DPU is therefore the sum of DPUs, while the total yield is the product of yields. Control points, visual inspections and tests, are defined in the control plan for each of the product types. In this example, we have several visual inspections, one ICT and one functional test, performed in this order. Visual inspection is performed as close as possible to the step generating the defect, and the defects detected are typically corrected on the spot. The problem is that it is very inefficient. It can only catch 60% of the defects. In this example, this means that out of the total 0.38 DPUs, only 0.228 will be caught and corrected, therefore 0.152 will escape this control. Visual inspection operators, if they are qualified to do rework, they will report the defect and correct it, otherwise the board needs to be taken out of the stream and sent for rework. In this example, we notice that 20% of the inspected boards need to be reworked, so we can calculate the workload required to do this. We must also be aware that the 20% worked boards will join the stream again and be re-inspected, so this means that the visual inspection workload will be for 120% of the boards built. ICT uses a bed of nails to contact many points in the board and is able to test the functionality of some components. If the test coverage is 80%, 0.122 DPU will be caught in ICT and corrected, and therefore 0.03 will escape. Finally, the functional test has a high test coverage, but the test is not able to pinpoint where the defect is, therefore faulty boards need to be analyzed and repaired by an expert through a lengthy process. In the case of ICT and functional test, 14% of boards will require rework, and this may require a higher level of skills, and it will take longer to identify and correct these defects. Again, reworked boards will need to be retested, adding to the test workload. At the end of this process, we have 15-20 faulty boards going to the customer out of every million. This is obviously unacceptable, so we can start looking at the main contributors to defects and the main escapes of our detection controls. We can look at different improvement alternatives with this simulator and estimate the effect on the final PPM going to the customer. Visual inspection has typically a low coverage, especially with complex products. As an example, try to find a missing component in this board. A simple compariscope has been used to detect these defects by presenting a picture of the suspect board, followed by a picture of a good board, alternating between the two. You can easily see missing component C48 flickering. This simple aid could allow us to increase the visual inspection coverage. Supposing that we are able to increase our inspection coverage, in our original example, from 60% to 80%, we can see the impact to the customer with our simulator. We can see a defect rate decrease from the original 1,520 ppm to 760. Our improvement actions are mainly directed to avoiding defects from being produced on the first place, but we can work in parallel on the improvement of the defect detection process. PTH insertion, being a manual operation, is the main contributor to defects. We can look at ways to add some Poka-Yoke's defect-proof devices, or look at ways to automate. Suppose we are able to reduce the PTH insertion DPMO from 1500 to 500. The result would be a reduction of defective products to 1120 ppm. Sometimes, it may be possible to redesign the product to improve its manufacturability. In our case, for instance, we may be able to eliminate manual insertion by replacing PTH components with SMT, which are automatically placed. If we are able to do that, defective products would be reduced from 5 to 768 ppm. In this simulator, process DPMOs come from measuring our current processes. Theoretically, they should be product independent, but in actual fact, they are not, some designs produce more manufacturing defects than others, and the process parameters for some products may not be optimized. When we try to reduce wave solder defects, for instance, we realize that there is, typically, a mix of component sizes on the board. When the board goes through the wave solder, typically at 250 degrees C, small components reach this temperature immediately, but large components take longer. This means that some components may be overheated, and others underheated, causing defects. We can find the optimal process parameters, solder temperature and conveyor speed, for each type of board with design of experiments. These are some conclusions. Understanding the different mechanisms in our value stream, which cause defects, is essential to eliminate the root cause, or at least, detect and correct them upstream. This simulation helps us focus on the main contributors of defects, in order to give feedback to those producing them. The overall process control plan defines the controls and tests along the value stream, in order to detect and correct defects as soon as they occur. The control plan needs to be updated after each improvement, in order to optimize resources. Analysis of defect escapes from our tests, detected further along the process, should help us increase test coverage of previous steps, and get to the root cause of defect generation. DPMO is a useful metric for process steps, and simulation allows us to estimate the DPU the customer will see. State-of-the-art DPMOs are very different for different processes and products. DPMOs from different processes, therefore, can't be compounded to obtain an overall DPMO. DPMO is for those working in a particular process, not for the customer. Yield and coverage measure the effectiveness of tests and controls in our control plan. You can see this article in Polyhedrica blogspot.